But let's start with a small film and pay attention. Please tell me if you see a difference between those two flights. Can you spot the difference? Wait, it's coming. All right. By now, you should have spotted the difference. This is more or less actually the same rocket. The engines worked. They deliver a lot of power. So why did one of them fail and the other one didn't? Well, previously, there was another rocket, a much smaller one. It worked without any problem for quite a long time. Then they built a bigger one, much bigger one. But one thing they did is to put a lot more power in the engines, but they kept the same inertial reference system, the same sensors if you want. So the feedback loop was faulty. The rockets failed to control the direction, and so it failed because there was a bug in the feedback loop. The control mechanism had been designed for a smaller rocket, and therefore it failed. So, in a sense, a much bigger engine without a proper feedback loop will fail. If you fix it, though, it works. And that's actually the second rocket. So why am I talking about that? It's because the key to optimizing anything, really, for stability and efficiency, is to have a great feedback loop. This is true in electronics. This is true in hi-fi. This is true for rockets and cars. This is true for companies and software development processes. AI is accelerating every function in the companies. We have more demands. We have AI-powered development that is more powerful than ever. It's just like a much bigger engine in a car or in a rocket. It's just like a much larger hi-fi amplifier. So we see more and more deliveries, but we need to have a much more efficient feedback loop to get the best out of AI. So today we're going to talk about what metrics we should monitor to monitor delivery, what actionable metrics we should optimize for, and we're going to see how Gradle helps with that. But first, let's talk a bit about the different types of metrics we have. We typically define 4 types: the effort, output, outcome, and impact. Of course, that's just a scale, but you get it. So the effort ones are about what people do, the time we spend coding, the number of meetings we attend, whatever. The output will be more about what gets produced, so the number of pull requests, the lines of code, the builds in a CI environment. The outcome metrics will be about the feature you produce, the developer satisfaction, and lead time or MTTR. And of course, the impact ones are bottom line revenue, customer satisfaction, success metrics in all 4 kinds. What truly matters, we all know that at the end of the day, is the business metrics, the impact ones. But it's kind of hard to reason about them when it comes to understanding the effect of an action we take and the impact on them. So it's much easier to measure the activity metrics on the left. Also, we can see that AI typically has a big impact on how much output we have. So those metrics are also in I would call that a dependency graph. In this example, if you use more AI, you're going to have more iteration on the code, hopefully more features, and maybe you're going to get more satisfied users. But on the other hand, the use of AI creates larger code, larger changes, which itself can impact and make it more difficult to understand failure, so PTR or MTTR for medium one. The leading metrics on the left, which are the ones that move really, really fast, they are close to the actions we take. They tend to be noisy. They can be used for tactical planning. They are easy to game, and they quite often can be vanity metrics. The lagging ones, though, they are more about business value, what matters really. They are close to, say, impact or outcome metrics. They are stable. They can be used for strategic directions. And remember this one, that's very important. They tend to be delayed. Example is, again, talking about MTTR, the time it takes to fix a problem in production will depend on the complexity of the code, but the complexity of the code will grow over time. It's going to take time before it has an effect. So, in particular, we have the famous DORA metrics. DORA metrics are not technically impact metrics, but research has shown that it's kind of difficult to have a successful company with not very good DORA metrics. In some way, they are the direction of the rocket. This is what you want to monitor. This is what you want to check. The feedback loop that we want to have at the end of the day is check for changes in the outcome of the impact metric, so typically DORA, take corrective action if need be, and then iterate. And in particular, we want to monitor, say, MTTR and check how it moves. I keep on mentioning MTTR because that's very important. It is, in fact, one that measures how good we are at correcting production problems. A longer MTTR is really important to look into. It can be due to code complexity, flaky product, flaky test, logging issues, infrastructure issues, and so on. So the problem is that we have a big problem. We have a big problem because we have a delay, as I mentioned. When we take an action, for instance, if we introduce AI in a system, it's going to take a long time for the code to become more complex, and therefore it's going to be more difficult to troubleshoot issues. You probably have experienced that input lag with a game. You know, you play a game, and something happens on the screen. You press a button, nothing happens. You press the button again, and then the game reacts. And of course, it's too late. Same thing happens with metrics which are delayed, for which we take action. It's kind of unstable. So we find ourselves in a difficult situation because we want to optimize for impact metrics. The DORA metrics are good proxies, but corrective actions are delayed. So this brings you to an unstable situation. So this is difficult to understand the root cause for a DORA metric moving. What can we do? Before I answer that question, I would like to introduce what I call developer TTR. Think about it. If you're a developer and you need to do something, you need to go there. You need to fix that feature or fix a bug. So you take one step in the direction of this change. And so you modify some code. And more often than not, you break something. You break tests, you break builds, maybe you make a performance regression or something. And it's going to take you a while to understand what goes wrong and go fix it. These are all the red builds. And then you go back to green. So as a developer, you have this notion of, say, local TTR or developer TTR, which is the time it takes in a normal cycle to produce some value. In fact, if you really realize, if you look at how a developer works, this time fixing problems or understanding the issues can be up to 70% of your time developing. That's quite a long time. So, by the way, this applies for developers on their own machines, but it also applies for CI, and both in the PR branches or the main branches. At Gradle, as you know, we work with a lot of customers who use Develocity to accelerate, troubleshoot, optimize, govern, and observe the development processes. And we have noticed something interesting. There are some metrics which are powerful proxies for DORA. The first one is build flakiness. It's kind of an equivalent of reliability. The merge time frequency to main or master, which is sort of an equivalent of deployment frequency. The duration of pull requests, which looks like lead time. The number of broken builds on main, which looks like failed deployments. And the developer pull request or the main branch TTR, which is sort of an equivalent of the MTTR. These relationships show that we have what I call the local DORA metrics, the DORA metrics at developer level, if you want. And in fact, they reflect the life of a developer. They reflect how easy that is for a developer to produce value on a day-to-day basis. Optimizing for them is much more actionable. Now we have a feedback loop that is a lot shorter. And as a company, we can look at them in a very easy way. Data is quite easy to collect. All the builds, if you can collect them, they are easy to reason about. And you can really quickly see the impact of a change you make in your infrastructure, in the way you develop, or in the way you review code. If a local TTR is too long, That's going to impact a lot of things in the actual DORA metrics, in particular the deployment frequency or the actual MTTR. So let's recap for a second. We want to use DORA metrics to track and optimize the proper direction of the company. But we need a more actionable loop, an actionable proxy, which is the output kind of metric. We can use the local DORA metrics for that. And in particular, the developer TTR measures the ability of developers to create value or to fix value on a day-to-day basis. And the distribution of this metric looks like this. The first thing is that no bug, no problem can be fixed faster than you can build the code. So there is 0 fixes faster than the build time. And then you got the clear problems, the ones which are obvious, then the complicated ones, the one where you sort of have an idea of how the system works, and you're going to make a test and iterate on that. And then the complex one where you first need to build a model of how the system works in your head before you can take action. Then for those who know the Canadian framework, there is also the chaotic problems where you have absolutely no idea what's going on. Using AI in the development processes, unfortunately, tends to move things to the right. AI tends to generate larger changes and many more of them. This is good in a sense, but it also creates a lot of pressure on a CI system. It also creates more queues in a CI environment. And because the changes are much bigger, it's harder to use caches. Also, when you do face a problem in a code and you try to fix it, it's a lot harder to interpret the code. So I don't know if you experience that, but when a developer looks at the code and tries to understand what's going on here, they tend to try to infer the intent of the previous developer. So, okay, this person wrote the code this way because they thought about this or that case. If a person wrote it, that's cool, but what if that's an LLM who wrote the code? So that becomes much more difficult. And at least for me, I have experience writing code 3 months ago with the help of an LLM, and then realizing that I didn't quite fully understand the logic of it 3 months later. So AI can make troubleshooting more difficult and more costly. So having AI to write code is great. It creates more code. But if it's written in a way that we cannot understand, then that's a lot more complicated. There is hope, though. We can leverage AI to make builds a lot faster, and I'm going to show you how afterwards. We also can select on the fly the tests that make more sense to run and disregard the ones which are not affected by the changes we made. But we can also use AI, and again, we're going to demo that, to find the root causes of the problems, to group the failures together when they have similar problems, similar root causes, and suggest solutions even to improve the code and the builds. Examples, we can tell developers, we can isolate root causes from the build failures, and we can group them, as I said. We can tell the developers if a test is flaky by just analyzing the past, or if maybe the product is flaky. We can tell developers if the problem that they face is due to their change or to some infrastructure issue. We can tell developers, okay, maybe you are experiencing that problem, but guess what? A lot of other developers in the same company are experiencing exactly the same issue at the same time, so maybe it's not your fault. We can tell them if something is actually happening on another branch, etc., etc. And we can even say, look, a similar failure was fixed that way in the past. Maybe you can try to fix it the same way. So as I said, faster builds, easier troubleshooting. But for an AI tool to be very useful, we need to have 3 things. It's normally something. The first thing is that you need to have great reasoning capabilities. The second thing you need is to have access to the relevant context and data. And the third problem is that you need to fix a problem that a person has or like an agent has. So you need a real use case. And this is where we can leverage the value of all the data that we collect in Develocity when we build. We collect dependencies, toolchain information, build performance, infrastructure logs, task and result, and a lot more. So now we're entering demo time. I'm going to show you a few films that show that from within IntelliJ, we built a plugin that will interact, will collect information from the builds, send them over to Develocity. And because this is within IntelliJ, the developers don't have to change their environments. This is where they typically live. We're going to use Develocity AI-powered failure grouping. And then in the third part, I'm going to show you how to interact with the MCP server that itself collects data from Develocity. So obviously, Gradle builds, and in the future, Maven and all the other tool chains. Develocity and Develocity plugin for, in this case, IntelliJ IDE. And of course, Develocity itself with failure grouping. Let's go. So here is IntelliJ. We run a build. And here we see, like the build has run, and we have cut the time here. And we can click, in one click, you can go directly to Develocity and find why is it that it failed. And I'm going to zoom in. And here you see there are two groups. Actually, there were 13 failures. But in practice, it's only two groups, one of 8 and one of 5 test failures. So in this case, Develocity tells you, hey, you don't actually have 13 things to debug. You only have 2. They have similar root causes, so the odds are if you fix those 2 problems, that's going to be fixed for everything. So developers can see really quickly the only 2 problems that there are. So they can fix, maybe they can pick the largest one, or maybe the easiest one. They can make their choices. The build scans, as you know, contain all the information you need to understand the builds. And now I would like to show you like how a developer would typically interact with both their IntelliJ IDE, but with an agent that itself will call MCP server from Develocity. In Develocity, we have the build scans, the test results, the performance data, the cache analytics, etc., etc. So a lot of information that can be helpful for developers to understand their builds. Here we go. So same thing, that's following the previous one. Hey, can you tell me why my build failed? And here it goes. It's going to contact the MCP server with a proper build ID. And here it's going to show you that, well, I can see a few problems here. And you see there's a problem with ByteBuddy, which is only experimental in version 23 of Java. And maybe we can ask it, okay, can you use the MCP server to identify which version of ByteBuddy I'm using? So the ID asked me, is that okay to call that MCP server? And here we go. Here's the explanation here. Maybe what you can do is enable the experimental version with Java 23. OK, go ahead, do it. We can fix it. And here again, the agent will be able to make the suggested changes so that the test can start passing. We accept the changes. And here we go. Now the next one is actually that's going to fix one of the 2 tasks that were failing, not the both of them. So maybe we can continue this interaction. Again, we're going to ask, hey, I still have a problem here. Can you help me understand what goes wrong and maybe fix it? And same thing is going to go interact with Develocity, collect a lot of information about what the build did, the type of run there was, what happened during the test. And now we see what the problem is, the suggested changes. We go accept the changes. and rerun. Success. Everything is good. But if you look at it, you will realize that one of the tasks still takes a long time. So what about we ask Develocity to help us understand why is it that this task takes so much time, and go fix it? Well, let's go. This is the equivalent of saying, hey, my build takes too much time. Can you help me make it faster? It actually works quite well these days. Please. And here again, connecting with Develocity, understanding what the problem is, making a suggestion, which we're going to be able to accept. So what I just showed you here is that as a developer, within your IDE, you can see exactly what happens in your builds. You can identify the problems. You can ask with an agent against the MCP server what goes wrong and go fix it. You can do a lot more. We're going to talk about it. But most importantly, you can also use it as an infrastructure team. So I used to drive a team in charge of CI environments. And I know that when you have a lot of developers, they tend to be unhappy sometimes because it's not stable. It is difficult to prioritize the right problems. So typically, here is a prompt. For this project, are there builds that fell like a day or two ago? And guess what? Yes, a few builds fell in the past. So I answer, yes, I want to see them, and here they are. And then I can ask, hey, what are the most common root causes for those problems? And here I get an answer showing me like among the latest, in this case, 10 builds, there were those main three things. So now, as an infrastructure team, I can realize that if one of them is an infrastructure issue, maybe I can go fix them. This is very powerful. So I don't know if you've been in an infrastructure team or CI team or whatever, is that it is really important to be able to look at a very large number of builds and identify the main sources of problems. This is what it gives you. We will continue to leverage all the in-depth information you find in the build scan. For developers, we'll get more and more integrated into the IDE using agents. We'll be able to answer questions like, what is it that's changed since my last successful build? What are the other developers experiencing at the moment? Do they experience a similar issue that I am? How did other developers fix similar issues? What are the most common issues and their root causes for me? What are my most common mistakes? For the central teams or infrastructure teams or CI teams, it will be like, what is it that people struggle with the most? What are the most common infrastructure problems? Do we see some failures happen more often than before? Are there new kinds of failures happening during this last 2 hours? And of course, we can be also more proactive. We can say, hey, here's how you could optimize your build and make it 5 times faster. Here's how other people optimize similar builds as yours. And of course, we can shift left governance and bring warnings to the developers and say, well, maybe you should not use this dependency because that's going to be rejected when it comes to deploying it in production. So as a summary, AI development creates great power, like for a rocket, but it also requires a great feedback loop. So developer TTR is able to track and optimize the feedback loop. If you track it, you should optimize for it. AI troubleshooting can streamline, supports, helps AI development. And by integrating the IDE, diversity, observability, and MCP server, we can deliver a developer experience that is a lot smoother than before. We cannot wait to see what you're going to be doing with it. With that, thank you very much.